So once we have learnt about the transformation of the inertia tensor, okay, we want to now understand what the principal axis of inertia at A is. So let's say that if an axis n is called the principal axis of inertia at A, if INS at A is equal to 0 for all s perpendicular to n. Okay, so remember we have just written INS over here. Okay, when this happens, when this INS of A is 0 for all s perpendicular and n, then you have the corresponding INN is called the principal moment of inertia. Okay, the corresponding INN of A is called the principal moment of inertia. Okay, now let's see 3.11. that was what INS is equal to IPQ NPSQ. So INS of A is equal to IPQ NS NSQ. Okay, NSSQ. Sorry, NP. IPQ. Sorry, IPQ. There can't be an S in Q. It will be NP and SQ. Okay. Now in this one, call this term. This will only depend on Q because the P will be repeated. So VQ, let VQ is equal to IPQ NQ and NP in this. Okay, then INSA will be written as VQSQ. This, if you remember, is just the dot product V and S. Okay, is equal to 0 for all S perpendicular to N. Okay, because that's what we require over here. This INS should be equal to 0. So once this is once we have allowed VQ to be like this, such that the dot product of V with S is 0, then this would imply that V will be equal to lambda n. Okay, because n is perpendicular to S, so this will always be 0. Now once you write VQ is equal to now this IPQ we can also write as IQP. Okay, so let me write that just because it's symmetric. We have already shown that before. Okay, now VQ will also be equal to IQP NP. This would mean that this is equal to lambda NQ. Okay, because V is equal to lambda n. Okay, this implies that now if you write it in the sort of extended form, okay, you can write it as IQ1 N1, okay, sum over the repeated index, IQ2 N2 plus IQ3 N3 A is equal to lambda NQ. Okay, this is equation 3.12. Now this 3.12 is essentially 3 equations. Okay, This 3.12 is actually you should also try to answer this part. Okay, how can I, Q, P and P be written as lambda n q? Not very hard, but you should try to answer that. Okay, now this 3.12 is actually selection of, I mean it's three equations, because q can take values from 1 to 3. So for q equal to 1, we will write I11a n1 plus I12a n2 plus I13 n3 to lambda n1. Now then this would be for q equal to 2, you have okay, plus I32 for q equal to 3. Okay, now this can be written in the matrix from these three system of linear equations as I11a, I12a, I13a, I21a, I22a, I23a, I31a, sorry, I32a, I33a. Then this would be n1, n2, n3 equal to lambda n2, n1, n2, n3. Okay, this also means that you can write it like this. So this is 3.13. So as it is obvious, this n is actually equal to the column form of n1, n2, n3. So to write that, just take the transpose of the row form. Now once you write it like this, it implies that n, and this comes from the linear algebra, which by this time you should have learned. If not, it will be done at some point in the immediate future. So n and lambda are an eigenvector and an eigenvalue of IA, since u and lambda are defined as eigenvector and eigenvalue pair of matrix B if Bu is equal to lambda u. So this comes from the linear algebra, and it's not something which theory of it is something which we don't really discuss in this course, but it should be something familiar to you by this stage. Okay, now you want to combine 3.10 and 3.12. So 3.12 is this one, okay, where VQ is written as this. Okay, now 3.10 on the other hand is INN, okay, because this is the principal moment of inertia. Okay, so with this, let me just write INN is equal to INN from 3.10 is equal to IPQ A NP NQ. Okay, now this value IPQ NP is actually equal to lambda NQ. Okay, so this is IQP NP is equal to lambda NQ, but this is also IPQ NP is equal to lambda, so this is symmetric. So that's why you have this as lambda NQ NQ or lambda N dot N. Okay, and this will be a lambda because this is a direction vector, so it has a magnitude of 1. Okay, so this is 3.14. So hence the principal axis of inertia and principal moments of inertia at A are respectively the eigenvectors and eigenvalues of IA at A. Okay, again it is known from linear algebra that there would be 3 eigenvalues. So this is something which again comes from linear algebra, that a real symmetric 3 into 3 matrix has at least 3 orthogonal eigenvectors EI star with 3 eigenvalues lambda I mean, if it's a real symmetric 2 by 2 matrix, then it would be 2 eigenvalues, lambda 1 and lambda 2. These results are not really specific to moment, so the inertia tensor. It's true practically for all tensors. Okay, of course our interest over here is only inertia, that's why we are dealing with it, but all these theories which we are discussing are true for all, as long as it is real valued and symmetric. Symmetry part we have already shown. Okay, it's just so happens most of the applications in mechanics, at least in the commonly applied terms, are symmetric. Okay, these tensors are mostly symmetric, hence we can utilize this property of eigenvalues and eigenvectors over here. uh, so that means that, say, if you have a, let me write the statement first and then I will draw the corresponding diagram, and then I will try to physically explain what is the importance of this principal axis is. So this means that the text in green shows that there always exists at least three orthogonal principal axes of inertia EI star at A with respect to which the inertia matrix takes a diagonal form with IA star is equal to lambda 1, I22 star is equal to lambda 2, and I33 star is equal to lambda 3. So this means that in the principal system, lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. Okay, and this is I11 A star so this would be 0, I22 A star 0, I33 A star. This is 3.15. So if you have E1 hat, E2 hat, and E3 hat, and this is the mass m. Okay, now I take up another coordinate system. Okay, E2 star, E1 star, and E3 star. Obviously this is all also mutually perpendicular, orthogonal. This is point A. Now what will happen is that any inertia tensor in black having all the 9 terms, which when transformed, okay, into this green coordinate system, will be such that you will only have these diagonal terms over here. So that's the meaning of it. So all the values are concentrated like this. So let me explain that with another example, perhaps something which can more easily be visualized, because tensor is somewhat harder to visualize for us at this stage. So let's take up a vector. Okay, let's call this vector as AI plus bj. Let me call it as x1 and x2. It's this x1 axis, this is x2 axis. So say this particular point is called ax1 plus bx2. Okay, now you know that you can transform this x1 and say x2 in this way, and then the same vector, okay, the vector itself does not change, only its representations will change. So now let me call this x1 dash and x2 dash. So this vector will now at the same place can be written as a dash x1 dash plus b dash x2 double dash. Okay, a generic transformation like this. Obviously it has to, the magnitude of the vector remains the same, so a dash square plus b dash square will be equal to a square plus b square. Okay, Now obviously a dash and b dash are the other two components of this vector in the blue coordinate system. Now what does principal system mean? It means that if I have a transformation like this, okay, if my coordinate system have a transformation like this, so this becomes your x1, let me call this as x1 double star and x2 double dash, okay, and obviously the representation of the same vector now will be a double dash x1 double dash plus b double dash x2 double dash, okay, and yet again this will be the same as a double dash whole square plus b double dash whole square, because the magnitude of the vector remains the same, okay, there's no doubt about that. Now but something really strange happens over here. In this particular case, this b double dash will actually be equal to 0, okay, and because you can see that this point lies entirely on the x1 double dash direction, so you will just write it as a double dash x1 double dash hat, okay. So definitely now under this particular transformation, x1 double dash is a principal axis, because the entire weight of this vector, the entire magnitude of this vector, so this value will be equal to this, okay, this value will be equal to, sorry, under root of this one, and same for over here. So the entire magnitude of this vector is lying along x1 double dash, okay, and that makes it as a principal value. Now can you think of what will be the weight or the magnitude of this vector along x2? It will be 0, right? Okay, so it will be 0. So this is one other interpretation which you have. So if you transform your say any tensor now, okay, a b c d, okay, I'm just taking a 2 by 2, and this is all symmetric, okay, this assumption of symmetric tensor has to be there. Now if this is transformed along a direction such that only the principal values exist, then it will have, say, a value only along a0 and 0b, or let me not use a and b, let me use l and m, okay, and these terms would be 0. One of them will be taking the maximum value, the other would be taking its minimum possible value, just like over here one is taking the maximum value and the other is taking a minimum value. So principle, so writing this I something like this is just one special transformation, okay, out of those infinite possibilities of transformations, this is one special transformation such that all these terms become 0 and only the terms along the diagonal exist, okay. So that's the overall idea about principal axis, okay. So that applies for many different cases, including the one which you have just seen. So let me remove that over here, okay. So the same we have just discussed over here. So if you have a IA written in black, it has to be specially transformed, okay, under some special transformation in which it becomes I star, okay, and that special transformation will make it look like this, in which the diagonal terms are only 0. Sorry, diagonal terms are non-zero, okay. So it will be, I mean, this is one of the exercises in your text through which you will be able to verify that if I x z of A is equal to 0 and I of yz is equal to 0, then z is a principal axis at A, meaning all the sort of so-called weight of the tensor will be lying along the uh, diagonal terms. Okay, so this is something which you must verify. Okay, this is one of the exercises in your text, so you should please do this. The proof of it is somewhat easier for us to do. Okay, now let's take up this omega. Okay, so let omega, this vector, in the omega I star ei star. Okay, now we want to write HA in terms of the principal system. So for this we must invoke this equation 3.3. Let's see how we can do that. So can we see 3.3? Yeah, I think we should be able to go back. Okay, so we want to write the moment of momentum about point A, and there you have it, 3.3. so HA is a vector. Okay, and this is written in this particular form. Okay, and in this matrix form, the three components of HA, which is HA1, HA2 and HA3, can be written like this. Okay, now you can imagine this, that if this is converted to a principal system, then you will not have this and this. Okay, you will only have the diagonal terms. So that is exactly what we are trying to do now. We are trying to work under a transformation in which only the principal components exist. So let me do that. So what I'll do is I'll just write equation 3.3 and HA1, HA2, HA3, I11A, okay, I22A, I33A. Now I am putting a star over it just to indicate that these are the principal moments. Okay, principal moment of inertia. And here it would be again omega 1, omega 2 and omega 3. Sorry, since it's principal system, so you have this. Now this as a vector can be written as I11A star. So I may be writing star at different places, but they are all the same. Okay, plus I22A star omega 2 star. So this has a vector, so it must be on the E1 star direction, E2 star direction, plus E3 star. Okay, so we have written the moment of momentum about point A in terms of the principal axis. Okay, this is equation 3.16. So we had already made that point that in general HA is not in the direction of omega, not even for plane motion. It will say if the direction is, it will be in the direction of omega if say HA IA omega, this is the generic one, okay, and over here you have lambda omega. So then clearly HA is in the direction of omega. Okay, so in this case, if IA n is equal to lambda n, or n is a principal axis of inertia at A. So only when n is the principal axis of inertia, then if omega is written as omega n, okay, like this, then only h will be in the direction of omega. HA will be in the direction of omega. We have other fancy ways of writing it as well. So HA is in direction of omega if, meaning if and only if, omega is in direction of principal axis of inertia. Inertia at A. Okay, so if you have, say, an example, omega is equal to omega E1 star. So every time you see a star, it automatically means it's a principal direction. Okay, so you have E1 star like this. Then in this case, HA will be equal to I11 A star omega E1 star equal to I11 I11 A star omega. Okay, because omega E1 star is this. So over here HA and omega are in the same direction. Okay. Now this locating the principal axis of inertia, as you can see, is very important for any given geometry. Why is it important? Because it really simplifies our use of this. Okay, and that it does by simplifying this from essentially 6 terms to 3 terms. I'm not saying 9 because it's a symmetric matrix anyways, so it should have 6 terms. So, and that makes it very easy for us to use this. So this relation of this rigid body with a rotation omega, so its moment of momentum can be related like this. So locating this principal axis is really very important. Many a times life is easy, so you can just look at the figure and then say it. But you have to somewhat be more experienced to identify this. So let's see what are the, can we look at the mass symmetry and then see what would be the principal axis. So finding principal axis of inertia by inspection. Okay, so there we'll study three methods of this. So you have, say, a normal to a plane of mass symmetry is a principal axis of inertia at its point of intersection, at its point of intersection with it. A normal to a plane of mass symmetry is a principal axis of inertia at its point of intersection with it. So let's see one example. Say if somehow again I'm somewhat challenging, I find it challenging to draw. So just assume that this is symmetric, okay, about a plane of symmetry which is somewhat like this. So this is a plane x y of mass symmetry. Okay, so you have y, you have x, and you have z. Now, being this plane of mass symmetry, it means that if you have a small mass dm at x comma y comma z, okay, and then you have this mass dm at x comma y comma minus z. Because of this symmetry, you will have say rho of x comma y comma z is the same as rho of x comma y comma minus z. So this is a symmetry about the xy plane, okay, and in this particular case you have to say that the izx will be equal to, how do you find izx? You should look at the equations. I think we have already derived this. Long before this. Izx. Okay, so izx is over here. So this is the integration of zx dm minus of integration of zx dm. And similarly, we'll be finding izy as well. Okay, so that would be equal to minus of integral yz dm. So let's do that. Okay, so okay, this is minus of m zx dm, okay, and this particular value would be equal to 0 because there is a symmetry about this uh, z and minus z. So every small mass dm over here, okay, would cancel out a small mass dm over here, okay, and that will keep on happening for all the masses. So this izx will be equal to 0. So you can also write this in the row form, okay, in which a small volume can be, say, written as rho dv, dm will be equal to rho dv, a small volume, and then proceed either. So either of them should be okay, but it will be 0. Similarly, I zy of A is equal to zy dm is equal to 0. Now, since these two quantities are 0, this automatically implies that z axis is a principal axis of inertia at A. Okay. Now this is sorry, I didn't draw, but this A is lying over here. Okay. So say this is the line of now if you take up some other say point like this of B, and it has the same mass symmetry like this, okay, in that case Z axis is not a principal axis of inertia at B. Okay, so I mean if it has to happen at B, then this plane of symmetry has to pass through that. Okay, just like it says over here, a normal to a plane of mass symmetry is a principal axis of inertia at its point of intersection with it. So B is not really lying on the plane of symmetry, and hence this value will not be Z will not be 0, and that will not be 0 because I mean all these things will not be 0 about B. So clearly, I mean if you have a thin plate, okay, thin plate, I mean it will not be very, so the point A and B will not be very different. Okay, for a thin plate it will overlap because this will be so thin that you will not be able to distinguish between any 2 points over here, and hence thin plate, all of this is true. The second situation which we have, if a body has 2 orthogonal planes of mass symmetry, say xz and yz, then at A of their intersection the axis y and x normal to these planes are principal axis, then y and x normal to these planes principal axis. So automatically if you have say y as your principal axis, you will say that I yz of A is equal to I yx of A is equal to 0, and this x is the principal axis would mean I xy A is equal to I xz A is equal to 0. This will automatically implies that I zx, okay, so these two are true separately. Now since this value is equal to I zx and equal to 0, and this is equal to IZY is equal to 0 because of this. This will automatically imply that Z is also a principal axis. Okay, so say you have a geometry like this first. Say you have a geometry like this. Let me draw the XYZ axis over here. So this is Y. Z, A, X. Okay, now if a body has two orthogonal planes of symmetry, XZ and YZ, so you can see that this entire body has your XZ and YZ as the plane of mass symmetry. Let's first take up the XZ plane. Okay, in terms of the XZ plane, this one is the direction of mass symmetry. Okay, and for the XZ plane, this is the direction of mass symmetry, meaning any point over here and any point over here will cancel each other out in terms of mass. Okay, similarly YZ is this plane, so let me just remove this. Let me now put it back. Now for YZ, you will have this is the direction of symmetry. So any point over here and any point over here across this YZ plane is 0. Similarly, over here, uh, this will be the direction, okay, of YZ plane. So both of them, sorry, not this one, this would be the direction. Okay, so all the three parts of this body are actually symmetric about the XZ and the YZ plane. Okay, okay, sorry, I'll just repeat this once more. I think I've got something wrong over here. I'll use a different color so that I don't confuse myself. Okay, so let's look at the XZ plane. This is symmetric about the XZ plane because all three parts of it are symmetric about this. Okay, so that would mean that this is the direction of symmetry of the XZ plane for this block. Okay, for this cylindrical pipe, anyways, XZ will be a plane of symmetry because this will pass through the diameter of it. And for this particular block, this will also be the direction of symmetry along the XZ plane. Now, if you look at the YZ plane, okay, so for the YZ plane symmetry, you will be looking across like this, okay, and for the YZ plane for the cylindrical rod, it will again pass through the diameter, so no problem. And similarly it would be over here. So this body has two orthogonal planes of mass symmetry, XZ and YZ. Then at A of their intersection, so A is this point where these planes intersect. Okay, X and Y are clearly normal to the planes, our principal axis. So Y will be a principal axis for this just by using this first part. Okay, so if you have a mass symmetry, then it will be true. So over here there'll be a x and y axis, which will be symmetric because of the other cases. So this is clearly true. Once this is true, you can use this part and write it as IZY equal to 0 because it's a symmetric matrix, and IXZ as IZX equal to 0. This will imply that Z is also a principal axis. So this is due to 1 above, okay, and this is due to this. So you have these three mutually perpendicular planes of axis of principal values, so principal axis. Now the third case is at a point on the axis of a body of revolution the axis of revolution and any line normal to it are principal axis. So say if you have a shape like this, okay, and you have y, x, z. At a point on the axis of a body of revolution, the axis of revolution, any line normal to it are the principal axis. So let me first draw the x, y and z are drawn, okay. Let this be called as axis of mass symmetry. Okay, and let me just draw this. I'll draw a different color. Right, where's the color not changing? Okay, so now let this come out like this. So this is the plane YZ of mass symmetry. Okay, now let's try to understand this. So if you have, say, this is the point clearly A, I mean I need not write it, but yeah, I should write it. This is A. So for a point A on the axis of revolution Z, okay, this is the point A. Yes, so this is the point A. You can see the axis of revolution is Z. Okay, A is on it. Okay, so now the density over here can be written as rho r comma Z. Okay, so rho is this body. Okay, so you can write this, describe this in terms of r and Z. Now if you have any axis x normal to the z axis is a principal axis of inertia, since the yz plane is a plane of mass symmetry. So if you have this plane yz as a plane of mass symmetry, then x axis is a principal axis. So this means that rho of, let's call it rho 1, because rho we have already written as something else. So x comma y comma z is equal to, now this rho can come in, r can be written as what, x square, a radial position on this can be written as x square plus y square comma z, and this is equal to minus rho 1 minus x1, sorry, minus x comma y comma z. Okay. So x, y and z will now be principal axis at A, because y, z and zx are orthogonal planes. So at a point on the axis of a body of revolution, A is that point, the axis of revolution and any line normal to it are principal axis. So the axis of revolution and any line, so Z is clearly axis of revolution, and any line normal to it are principal axis. So both x and y are normal to it, and hence they are the principal axis. So we have seen why it is the case, and you can see how each of these points actually uses this idea of a mass symmetry, either in a direction or about a plane. So the first one was actually along a particular direction, the second used that along a particular plane, and the third one is just utilizing the one along the plane to say that if z is a principal axis, then x and y will also be principal axis, and because of the symmetry of this problem, ixx will be equal to iyy about A. So this you can verify, check the formula of what ixx and iyy is, and you should be able to get an answer to this question. Okay, so do this, check. So the next we should take up say the principal moment of inertias. Consider special cases. Special cases equal to or all. Principal moments of inertia. Inertia So you have, say, I11 of A, okay, this I11 and I22 and I33. So let this one special case be that I11 of A is equal to I22 of A. So this would mean that every axis n is equal to n1 e1 hat plus n2 e2 hat is a principal axis at A. So for any s perpendicular to n, you will have ins will be equal to 0. So this would be iij a nisj. You can use now the chain rule. That would be I11a n1s1 plus I22a n2s2. Since I11 is the same as I22, you can just take I11a common and write it as n1s1 plus n2s2, and this is equal to 0 because this is equal to 0 for every s perpendicular to n. Okay, and this means that I11a is n dot s. This is equal to 0. So INN will be equal to IIJ A NINJ I11 of A N1 square plus I22 of A N2 square. Since I11 is the same as I22, let's take it outside, and this is N1 square plus N2 square, and this will be equal to 1. Okay, because this is just the magnitude of your vector and direction vector, and that's always 1. I think we also got it at a place where lambda was coming in. So lambda into n1 square plus n2 square plus n3 square, that would be equal to 1. Okay. Hence all directions n at A normal to E3 are principal axis. Of inertia at A with the same moment. With the same moment of inertia I11 of A. So you can think of a example of this particular case. Okay, the second case which you should take is that if you have all of these principal values equal to each other. So for any n for any n and any s such that one should have ins of A is equal to Iij A n Isj is equal to I11 of A n1 s1 plus n2 s2 plus n3 s3. And I and n of A will be equal to Iij of A n I nj. This would be equal to I11 of A n1 square plus n2 square plus n3 square equal to I11 of A. Okay, because we'll just take the terms common over here. Hence, all directions at A are principal axis of inertia at A. With same moment of inertia I11A. So the importance of this is, like, if you have, say, any body and you have, say, a point A, and you just somehow magically found that I11 of A is equal to I22 of A is equal to I33 of A. Okay, of course you can have other components as well, we are not concerned about that, but these principal, if these values, if the normal principal moments of inertia are same, then you can easily find out their principal axis. Okay, so if this is, for example, the case, then all directions at A are principal axis of inertia at A. And if you have only, say, two of them same, then you can say all directions at N which are normal to E3. Okay, because this is true. And similarly, if I11 is equal to I33, then it would be normal to E2 and so on, our principal axis. So this is sort of helpful in trying to identify the principal axis for us. Okay. So one of the other things which we normally learn about is the so-called parallel axis theorem. Parallel axis theorem. So this is just another way, I mean, to find the moment of in the inertia matrix, if you already know the inertia matrix in some particular direction. Okay, so let's see how this helps. Perhaps you are already aware of it. So if you have this, okay, a body of mass m, and C is what you already have. Okay, a point, this is Tm, this is point P, this is A, x1, E1 hat, x2, E2 hat, and x3, E3 hat. Okay, now from this point A you have this point P which has coordinates say of xi in the xi direction. Okay, this vector will be RPA. At C you have say another system. Let me call this as, okay, let me use this. So P of xy means it's in the coordinate system of A. Now I'll draw another coordinate system in a different color. Oops. I'll draw another coordinate system, say over here in what x. This is called x2 bar. This is called x3 bar. This is called x1 bar. Now the coordinates of this point P in this blue coordinate system are xi bar. Okay, and from over here you call this as RPC. Okay, so now let's sort of go through this working. Now what does this theorem tells us? It tells us that it gives the it gives the relation to find I of A at point of interest A from the known IC at center of mass C. So for most bodies, at least symmetric bodies which we'll learn about, IC is very commonly known, okay, because it's perhaps the easiest to calculate. And if you know that, you may want to use say HA equal to I of A, okay, into omega. Okay, you may want to use this about a point A which is not C. Then how do you proceed? Okay, so you have to just find this, and that is something you can find using this IC. So let's see how that can be done. Let me write this from the known, from the known IC at the center of mass C. Okay, okay, so consider two parallel axes. Xi at A and xi hat at C. Okay, C is the center of mass. So these are two parallel axes, the blue and the black ones. Now RPA can be written as xi ei hat. RPC can be written as xi bar ei bar, okay, and RCA can be written as xci ei hat, okay. So now if you want to write this m xi bar dm, okay, it's the position of P in terms of the blue coordinate system, which is fixed at C. This will be equal to mx ci, and this will be equal to 0 because the center of mass is like this. Okay, so this value is 0 because it is at C, xci is equal to 0. This implies that RPA is equal to now RPC, the triangle will construct, plus RCA. So let me draw RCA. I haven't really drawn that. Okay, this is RCA. So far so good. This implies that so just write this vector RPA like this, RPC like this, and RCA like this. Okay, we will be able to say that xi is the same as xi bar plus xci. Now, one of the good things, about this is that you want to write it, say xi ei hat equal to RPC's xi bar ei bar plus xci ei hat. Now ei bar is the same as ei because it's parallel. Okay, that's why you can sort of write that xi minus xi bar minus xci into ei hat is equal to 0. Since this is valid for all ei's, this means that this particular thing must be 0, and that's the reason we are writing this. Okay, so that's one thing which we have sorted out of the way. Now write I11 of A. This, as you know, can be written as x2 square plus x3 square dm. Now x2 square we want to take from here, so x2 we want to take from here, so that would be, what is x2? It will be x2 bar plus xc2 whole square plus x3 square would be x3 bar plus xc3, okay, whole square into dm. So let me write it as a square bracket. We have used this, we have just put I equal to 2 and 3 respectively in this one. Okay. And this particular thing can now be written as we'll just square it and add the terms together. They should now give us x2 bar whole square plus x3 bar whole square dm plus xc2 square plus xc3 dm plus 2x plus 2x c3 c2 first and then the c3. M would be x2 bar dm plus 2xc3 m x3 bar dm. This is equal to I11c, this one, plus m into xc2 whole square plus xc3 whole square. Okay, and the other two quantities would be 0 because x C2 and x C3 are 0. Remember over here, because these are the coordinates of the center of mass. Okay, so this would be equal to 0. Sorry, not this one. Okay, so this is m, this integration is done, so this is sorted out. So you have to think of, yeah, I think it's what this particular term, okay, should be in red. Nope. This somehow does not appear over here. Okay, so I11C. Okay, so try to figure out what has happened over here. Okay, x2 bar dm and x3 bar dm. Okay, what has happened over here? Similarly, you should proceed by writing, say, I12 I12 of A is equal to minus of m x1 x2 dm. x1 x2 again comes from over here, so put I equal to 1 and then I equal to 2 and then write those two terms. So this would be minus of x1 bar plus xc1 x2 bar plus xc2 dm. This would be minus of m x1 bar x2 bar dm minus xc1 xc2 dm minus those two other terms would come in, minus xc1 x2 bar dm minus xc2 x1 bar dm. Okay, so I think the answer for this one is clearly over here. Okay, so this term is actually equal to 0, and similarly this and this will also be equal to 0. So you would have a I12C minus of m xc1 xc2 Okay, now just keep on repeating this. In fact, you should do at least a couple of more, say I22 and I23 or I33 or I31, couple of more, just to see that you get all of it. So I'll write all these answers together. Now what I'm doing is I'm trying to write each of these components of the inertia matrix at A in terms of what is known at C. Okay, so this is known and this is known now, because so xc2 and xc3 should be known to us, and I12 of A is equal to I12 of C minus of m xc1 xc2, and then we can write I22 of A is equal to I22 of C plus M xc3 whole square plus xc1 whole square. I23 of A is equal to I23 of C minus mx c2 xc3. Okay, this is equal to I33 of C plus m of xc1 square plus xc2 square. C1 of A is equal to I31 of C minus m xc3 xc1. Okay. Okay, so this is a 3.17. Okay, all three of them, and it essentially gives us this inertia matrix at a point of interest A in terms of a known inertia matrix at the center of mass. So I of A is equal to I of C plus inertia matrix at A for discrete mass m at C. Remember, we had learned before that if you have discrete masses m1, m2, m3, m4 and so on, then you have to add an additional term. Okay, so this expressions which we have just derived looks as if you have IA plus IC plus an inertia matrix at A for a discrete mass, one single discrete mass m at C. Okay, so this is how it looks like, and this can also be written. Now let me just draw one more term over here. Let me just draw this, extend this, and let me extend this. Clearly this is perpendicular because x2 bar is perpendicular to x2 and x1 bar is x3 bar is perpendicular to x3. Let this distance be d3. Okay, from over here till until here. Okay, now we can write that can write that I33 of A is equal to I33 of C plus m into D3 whole square. Okay. And how do we know that? Let me just say this. So D3 whole square is equal to xc1 square plus xc2 square. You can see that over here. So this D3 is equal to xc1 whole square. Okay, this one xci. Okay, so xc1 whole square plus xc2 whole square. So this is the origin. This is xc1 comma xc2 comma xc3, and d3 over here will clearly not be away by xc3. Okay, so it will be xc1 square plus xc2 square. So this is distance of C from x3 axis at A. Okay, now this can be written over here I33. Similarly, INN can be written as INN of C plus MDN square. So d1 square consequently will be the distance of C from the x1 axis at A, and so on, and INS is equal to INS of C minus of M XCN XCS. This is 3.18. Okay. So if you have, for example, point A in this direction is N, okay, and then you have this S, and then you have B, C, then you can have this as dn. Okay, so the most general form would be that this particular distance will be xcn, this would be xcs, so P is projection of C on NS, so C is over here. So this is the most general form, and you can write basically either 3.17 or 3.18 if you want to write in terms of d1, d2 and d3. Okay, so you have this dn which is common over here, so either of them are okay. So one good thing about parallel axis theorem is that it's not really valid for any 2 points. One of the points has to be the center of mass. Okay, for example, if you have 2 points A and B which are not center of masses, then you cannot write A1 in terms of somehow IA in terms of IB. Okay, you have to, what you have to do, you have to convert this IB, okay, in IC, and then IC you have to use to find IA. Okay, so that's how one has to proceed. You can't like just do it for any 2 points. Then again, I mean, if you have to find, say this is the C, this is A, and you have these two parallel axes, so this is known, and now you want to find IA dash, say in this dashed system. So you have to first find IA using IC plus those terms, then you have to transform this IA dash using IA. So you have to apply a transformation matrix, APJ, AIJ, whatever it was. Okay, I think we have seen enough of it. So first use the parallel axis theorem to come from here to here, and then do this transformation. Okay, so lastly we can derive some of the inertia matrix for symmetric bodies, and a couple of them we can derive, the rest I can just write the expression and you should be able to derive. So let's discuss this inertia elements. for some symmetric uniform bodies. So let's take up a thin rod first. So you have something like this. You have, say, this is the center of mass, okay, and you have, say, I'll draw the X, and you have the Z, and you have the Y. Now take up a point A. So on this point A, you have another coordinate system, say 1, 2, and 3. Okay, so that's there. Now let's take up so the length is L, mass is M. Let me use another ink over here. Thin rod of length L, mass M. So it's a one-dimensional distribution of mass over its center line. So A is shown, C is shown like this. Point B is over here, point D is over here. Okay, at A and C, any axis normal to X axis is a principal axis. So at A and C, any axis normal to X axis is principal axis. Now can you recall why is this true? So we had studied, remember, 3 cases of mass symmetry. So please think of the reason why this must be true in terms of that. So please pause the video, and only when you are confirmed that at A and C any axis normal to X axis is principal axis, only then you should move ahead. So over here, for example, take up this small element dx, okay, and well, L by 2, this distance from the center line is d. So this can be 1, 2 and 3, 1, 2 and 3. Okay, so this is dx, and it is located clearly at a distance x. Come over here. Now since at an A and C any axis normal to X axis is principal, so let me just write out first Ix about C, that is equal to 0, Izz about C. So this is true because of the symmetry, and then Izz of C is Iyy of C is equal to x square dm. Remember, it's a 1D element. Okay, so it's a 1D element, so Ixx of C would have terms of y square and z square, so that's why this will be equal to 0. And over here also you will have, say, x square plus y square and z square plus x square, but z squares and x squares are 0 because it's a 1D element, so you are only left out with this. Okay. This can be taken as minus L by 2 to L by 2 x square m by L, mass per unit length, into dx. Okay, that is dm. So dm is equal to, say, mass per unit length into dx. This would make it as 1 by 12 ml square. So about the center of mass, this is true. Now, can you use the parallel axis theorem to find Ixx about B? Let's try to do that. Ixx about B is equal to Ixx about C plus md square. Okay, this would be equal to md square because Ixx about C is equal to 0. Similarly, Iyy about B would be equal to Iyy about C, okay, plus something which is actually equal to 0, okay. So this should be equal to 1 by 12 ml square. So please try to think, why is this 0? What is this term and why is this equal to 0? So this is the distance of B, okay, along which direction? Just like over here, D is the distance along the D is the distance in the x1 direction. Similarly, over here, this has to be a distance from the 2 direction, okay, of this. But since it's a 1D object, that's why you do not have this. So please really be clear about all these things. Okay, and similarly Izz of C will be equal to Izz of C plus m d square. Now this is again the distance along distance of this point C from the x3 axis, okay. So that would be equal to this term. So m l square by 12 plus md square. Okay, so I hope it is very clear that this point B is just below this over here. Okay, I think I have drawn it like that, but okay, fine. So be clear on these terms. This term, this term, and this term. Even though it's md square, but you should exactly know from which axis to measure. Over here it's quite simple, but it won't always be like this. Okay. Similarly, you can write this Ixx about A point. Okay, A is at the corner of it. You can see that over there. So Ixx, sorry. Ixx at A is equal to 0. Izz of A is equal to Iyy of A is equal to Iyy of C plus ml by 2 whole square. This is equal to 1 by 3 ml square. Okay. Fine. So when all this is done, so you now know the inertia values at the end of the rod and at the center of mass of it. So end of it has been found using the parallel axis theorem. Now let's take up a thin rectangular plate. So let me draw that first. One, two, and three. So first let's try to sort it out at C. Okay. This is say O, and this length is A, this is B. So this is modeled as a 2D distribution. Okay, so it will be mass per unit area divided by a small area. So let's see. So the planes x, y and x, z. So x, z are planes of mass symmetry through A. So what we do is we divide it into a small strip, this area into a small mass dm, and try to write the value of say Ixx of C, that will be equal to m into 1 by 12 b square dm. So this 1 by 12 is coming from over here. Okay, sorry, Ixx, where did it go? Okay, and this can be written as 1 by 12 mb square. So you can have similarly Iyy of C as 12 ma square. So these are all the expressions which you can now solve. I mean, you just have to apply this formula Ixx. You have already seen what it is. Okay, so you can just apply that directly. So this is about C, and similarly you will have about Z is equal to Ixx plus Iyy of C is equal to 1 by 12 m a square plus b square. Okay, so let me start writing from in red from now on. Okay, so you can like verify this, and similarly if say you have to write it about any point O. Okay, so I will just write it as Ixx of about O would be equal to Ixx C plus m into b by 2 whole square. This would be mb square by 3 Iyy about O is equal to ma square by 3, then Izz about O will be equal to Ixx about O plus Iyy about O equal to 1 by 3 m a square plus b square. Izx of O is equal to Izy of O is equal to 0. So I of xy of 0 O is equal to Ixy of C minus m into x co y co is equal to minus of m half a half b, but not equal to 0. Okay, this automatically implies that xy are not principal axis at O, because if it was the principal axis of O, then I mean this Ixy at O should have been equal to 0. Okay, so this is how you can find out, and you must do the rest of it on your own. Okay, so for example, for a cuboid, okay, then you can do it for say so about the center of mass, for example, Ixx of C, this could be equal to, so I'm not writing because then it will have symbols like a, this length of this cuboid along each edge is a b c, and then it will be lengthy expressions to write, but you should be able to do all of them. Okay, and not just about this, about a point O which is say on the corner of it, using parallel axis theorem. Then you can have say for a, let me do one of them now, which is thin circular ring. So x, y, z, the mean radius is r. Let's first try to write it about C. So the mass is m, okay, and it's modeled as a 1D distribution of mass. So I z of C is equal to m x square plus y square dm. Okay, this will be equal to r square. Since it's 1D, so the difference between say from this mid, so until here it is r, so this distance and this distance are negligibly small, so that's why we don't distinguish between them. So this is r square into dm is equal to mr square. Okay, and Ixx C plus Iyy of C is equal to Izz of C. Okay. When you have few symmetries, you can also use the so-called perpendicular axis theorem, and that also makes it quite easy. Okay, just take a small mass and sort of integrate it over. Okay, so thin circular ring is done, and yeah, then you can, so once the thin circular ring is done, you can also repeat it for several other cases, like thin circular cylindrical shaft. So I'm writing it in red because these are all somewhat exercises for you to do. And then you have a thin disc, Izz for this should be equal to mr square by 2. Then you can have a solid cylindrical solid circular cylinder. Spherical shell. Okay, thin. And then finally you can have a sphere of mass m. Okay, so all of these are things which you can do, and then you can also do it, say, for a half disk or a half cylinder or a half sphere and so on. So that helps us understand these concepts more clearly. Okay, so that's where we can end our discussion on the finding this inertia for some symmetrical bodies.